Hello everybody and welcome. In today's video we are going to be talking about the Incenter, the Centroid, the Orthocenter, and the Circumcenter of triangles. So let's just dive right into it. Here let's draw a triangle. Here we have some triangle. And let's start with the Incenter. So the incenter of a triangle is defined to be the intersection. It's the intersection of our three angle bisectors. So we're going to go from each of our angles and we are going to split our angle. We're going to bisect it. So if I'm going from the top here, I want to draw a line down such that it looks like it's going to split that angle in half. And I'm just going to do my best to do that. Here, make sure we really start at the center. Okay. Here we go. There we are. And so this intersection point is our incenter. Something else that's interesting about the incenter is that if we draw or put in a inscribed circle in our triangle, and so an inscribed circle is simply a circle such that it's a circle such that it's tangent with all three of our sides. So here, let me put it in and clean it up again. Make it really look like a circle. Okay. Here we go. Here we go. If we have an inscribed circle, then it just so happens that the incenter is also the center of the inscribed circle. And my picture may not be perfect, but if it was perfect, then the intersection point would also be the center of the inscribed circle. Next up, we have the centroid. And the centroid is the intersection. It's the intersection of our three medians. Of the three medians. So let's draw our triangle. Again, let's just draw a triangle. So here we have some triangle. Now a median is such that you go from your vertex, and where do you go from your vertex? You go to the midpoint of each of your sides. So right here appears to be the midpoint of this bottom side. About here seems to be the midpoint of this left-hand side, and roughly here seems to be the midpoint of this right-hand side. So let's draw lines from the opposing vertex to these midpoints of our sides. And this is how we construct our medians. And then the intersection of these points is our centroid. Now something interesting about our centroid is here, let's label these points. We'll have point A, B, and C, and point D, E, and F, and we'll call our middle point P. So our centroid is point P. So something interesting about the centroid is that length AP is going to be equal to 2/3 of the full length AE. So that would imply that the length PE is 1/3 of AE. Oops, I wrote B of AE. And then, of course, that AP is equal to twice the length of PE. So if we threw in some numbers, if AP was 6, let's say, then this shorter length here must be 4. All right, because, or I'm sorry, I already messed up. It wouldn't be 4, it would be 3. Because AP is twice the length of PE, and it is 2/3 of the total length of AE. And this relationship holds no matter what endpoint we come from. So if this value, if PD was 4, then what would CP have to be? If you said 8, you got it perfectly right. CP would have to be a value of 8. So there is your relationship for centroids. So next up we have the orthocenter. And the orthocenter is defined to be the intersection of the 3 altitudes of your triangle. And something interesting about the orthocenter is that for acute triangles, it will be on the inside of the triangle, just like the incenter and the centroid. However, for right triangles, it's actually going to fall on the triangle, and for obtuse triangles, it will actually fall outside the triangle. And so it may seem as a little bit of a misnomer for the center of your triangle to be outside of it, but in the case of the orthocenter, it actually can be that way. So let's start by our acute triangle example. So if we have an acute triangle and we are looking to draw the altitudes, the altitude is going from your vertex and forming a right angle with the opposing side. Now the opposing side, we want to imagine that it extends out, and wherever it intersects this line would be the orthocenter. Okay? However, with the acute triangles, as we already said, it's going to fall inside the triangle, so these lines aren't as needed. Here we want to intersect this side such that it's a right angle. Looks like to be right there. And then for this last one, we can see that this is our intersection point, so this would be our orthocenter. Again, all of these angles will be right angles because the lines that we've drawn are altitudes. Okay, so next let's look at our right triangle. Where would the orthocenter be on our right triangle? I have already kind of told you that it's going to fall on the triangle, but let's find out where. Maybe pause the video and see if you can figure out where the orthocenter would fall on a right triangle before I do it. I'll give you a couple of seconds. Okay, so for the right triangle, notice how the altitude of our top vertex is just the same as this line. And the altitude for this right vertex is the same as this bottom line. And then the altitude for our top vertex going up to meet at a right angle with the opposing side. Well, where's the intersection point? It's at your right angle. So for a right triangle, the orthocenter will always be the point where your right angle is, okay? And it doesn't matter how your triangle is oriented. If you have a right triangle, this is a ugly triangle, but if we have a right triangle right here, this point would be your orthocenter. Okay, let's lastly look at the orthocenter of an obtuse triangle. So here we have an obtuse triangle. And now I am going to draw these lines so we can really see where exactly our orthocenter will land. And here we need this last line here. Hopefully I have enough space for this all. Here I'm going to clean this up just a tiny bit. Okay, so if we drop an altitude from this vertex on the right and we want to drop it to the opposing side, where can we go on this line such that we have a right angle? We're looking for a right angle. Bam, it looks like this is a right angle. So we're going to extend our line out just in case. Going from this vertex here to this opposing side, where is our right angle? Bam, here's our right angle. Now really I need to draw this line quite a bit further, so I'm going to draw it all the way out. I can see I may be in the way for this problem, so I'm just going to remove myself for now. I'm going to redraw this first vertex, this first one we drew, just to make it longer, extend it out all the way. So it's the same line. And then from our top vertex, we're looking for a right angle upon this line. And we can see that our right angle is about here. And so this intersection is going to be the orthocenter for our obtuse triangle. Look at that. It's way out here, but that is our orthocenter. Let's continue forward for our last one. So our last one is the circumcenter. We have the circumcenter. And the circumcenter is described to be the intersection point of our three perpendicular bisectors. So, and again, just like the orthocenter, the circumcenter is in different locations depending on if your triangle is acute, right, or obtuse. And it has the same features in that for acute triangles, it will be on the inside. For right triangles, it will be on the right triangle. And for obtuse triangles, it will be outside the triangle altogether. Now, a circumcenter is actually interesting in the fact that a circumcenter is actually described to be the center point of a circle that is circumscribed, that circumscribes a triangle. And so it's kind of the opposite of the incenter. So a circumscribed circle is such that it's like this. It touches the edges or the points of your triangle. This is a triangle which is circumscribed by a circle. You know, the language is kind of funky, but this is what it is. And so we expect our circumcenter to fall at the middle of our circle, and that's about here. Okay. Now my picture is not drawn to scale, so it might not be perfect, but let's see if whenever we draw our perpendicular bisectors, it intersects at this pink dot. Okay, so again, a circumcenter is the intersection of the perpendicular bisectors. So we want to find the midpoints of each of our lines. This appears to be the midpoint of our long diagonal here, it appears our midpoint's about right here. And the midpoint of our left-hand side appears to be about right here. Next, we want to draw just a line that is perpendicular, so straight up. So it doesn't necessarily hit the vertex. As you can see, this line doesn't hit the vertex of our triangle at all. We just want to make sure it's a right angle and that it's a bisects the side lengths or cuts it in half. And so here we have it. These are all our perpendicular bisectors such that these are right angles. And it did do a pretty good job at hitting that pink point. So this is the circumcenter of our triangle. Now, this was an acute triangle. What about a right triangle? So let's clean up this picture. Let's clean up this picture. I'm going to erase these lines. I'm going to erase this triangle. Here, let me erase these as well. Okay, so a right triangle, let's draw a right triangle in our circle. Here we have a right triangle. Again, we want to find the midpoints. That looks to be the midpoint. That looks to be the midpoint. And this looks to be the midpoint. And then we can draw our perpendiculars. So here's perpendicular. With this one, there's a perpendicular. And this one, here is a perpendicular. So notice that for a right triangle, the intersection is again the center of our circumscribed circle. Of course it is. That's the definition. But it also falls on the middle of your hypotenuse. Okay? The circumcenter for a right triangle will always be the midpoint of your hypotenuse. Okay? Just like the orthocenter was over here at the corner, for a right triangle, the circumcenter will always be the midpoint of your hypotenuse. Excellent, excellent. And then lastly, let's check out a obtuse triangle. Let's check out an obtuse triangle. So I'll erase this triangle. So let me make an obtuse triangle. So here, so this is an obtuse triangle for sure. And let's mark our midpoints. So our midpoint appears to be about right here, about right here, and about right here. This looks pretty good. So if we go to draw a line that forms a right angle with our side, where does it end up being? Okay. Here's a right. Seems like our right angle is a little lower. Yeah, that looks to be a good right angle. I'm actually not quite happy with this one. Okay, here, distance. I think this line maybe more start here. We want a right angle. There we go. That looks good. And we want a right angle from this point as well. So here we have it. So this point here, again, it's the center of our circle. And these are all perpendiculars. For this third line, I didn't draw it going into the triangle, but of course, it extends in both directions. And the intersection point happened to be on the outside. And again, these are all perpendiculars. So these are all right angles from the midpoints of each side. And we found our orthocenter to be right here, right where it's supposed to be, in the center of the circle. Excellent. So as a quick recap, let's go back to the beginning and do a quick recap. We had our incenter, which was the intersection of our three angle bisectors. The unique thing about the incenter is that it's the center point of your inscribed circle, so the circle on the inside. Next, we had our centroid, and our centroid is the intersection of our three medians. The medians are the midpoints of each side of your triangle. However, we're not looking for it to be a perpendicular. We're going from our angle, from our vertex, to the center to the bisecting point of the side across from it. Okay, and then our centroid also had these characteristics with the lengths of the lines, whereas the longer part is 2/3 the total length, and the shorter, meaning the shorter part, will be 1/3 the total length. And again, if this is x, the shorter length is x, then the longer length would be 2x. Excellent. Then we had the orthocenter. Remember, for the orthocenter, it's going to be in a different location, whether it's an acute, right, or obtuse triangle. This was our example for the obtuse triangle. Here I'll remove myself again. We found the intersection point to be right behind where I was, right here. And again, the orthocenter is described to be where your altitudes meet. It's the intersection. It's the intersection of your altitudes. That is your orthocenter. And then lastly, we had the circumcenter, which is the center of your circumscribed circle from your triangle. That's a lot to say. That's a mouthful, isn't it? But it's found by placing your perpendicular bisectors, and their intersection point is the circumcenter. As something fun to leave you guys with, I wanted to also mention there's something called Eulers Line, and it's actually been proved that if you take the circumcenter, the orthocenter, and the centroid, they are all three of those points will be collinear. Now, it does not include the incenter, so I didn't forget to leave it off. The incenter isn't a part of Eulers Line, but the centroid, the orthocenter, and the circumcenter is a part of Eulers Line. And let's do a quick example. I'm going to make this real quick. I'm going to use a right triangle just because right triangles are the easiest ones to deal with, but this is actually true for any triangle, that the Eulers line is a line that is made from, again, the centroid, the orthocenter, and the circumcenter. So here, if I draw a right triangle, here we go, then we know, what do we know? Well, we know that the orthocenter will be right here at the 90-degree mark. We know the circumcenter is going to be halfway between, it's going to be half of our hypotenuse. It's also going to be the center of our circle. And then so we only really need to find the centroid. And recall that the centroid is the median of our, is the intersection of our median points. So let's cut these sides in half. About here, about here, about here. Seems to be about right. And let's draw up our lines to the opposing angle. Drawing a line from the opposing angle. And here I'm going to clean up this line just a little bit. Seems like the might have had the center just a tiny bit off, maybe a little bit more right there. Excellent. There we go. There we go. And you can see that these 3 points are collinear. And this is called Eulers Line. So just something fun I wanted to leave you guys with. Hope you guys learned something in this video. If you did, let me know down in the comments below. Thank you for joining me. Hit that subscribe button, and I'll see you in the next video.